So now let's see the multi-perceptron architecture. Okay, multi-perceptron architecture. So this is like an example we have seen for the ecolic pitch neuron. So we would see similar kind of example, or to be more precise, we just want to see how multi-perceptron is going to solve for X or X NOR, because this was one of the problem that the single perceptron was not able to solve. Okay, so before that, we have to add one more hidden layer on the perceptron, so single perceptron. So earlier there used to be just a single perceptron. Okay, so X1, X2. Okay, this is the. So initially this was like there was only one layer. So this as the output layer, because this is directly connected. I mean this neuron is just connected with the output, so that's why it's it's more. So it's more. So its job is mostly to output this value, like whether the neuron will fire or not fire based on the different values for the input. So let's say this is the output layer. So now, so in multi-perceptron, what we'll be doing is like we'll be adding one more layer in between the input and output layer, which is known as hidden layer. Okay, so it should be. I'll just try to make some rough sketch right now. Okay, X1, X2, and there would be like some hidden layer. Okay, so they will be like going on both the neuron, and this is the output layer. This is going to give Y, which is either 0 or 1. Okay, yeah, so this is. Okay, so let's say this is input layer. This is output layer, input, output layer, and this is going to be hidden layer. Okay, so now for different inputs, there are minimum neuron that has to be in hidden layer. Okay, that is going to be 2 to the power n. Okay, so for if this is the input number of inputs, okay, and this is or let's say perceptron. As for now, perceptron in hidden layer, and this is the minimum. Okay, so minimum, because it can go like here we have like defined 2, but here we can go with a lot of perceptrons. So the more the perceptron, the more it will be easier to learn the function. Okay, but the minimum perceptron that we need is going to be 2 to the power n. Okay, for single input, this is going to be 2 to the power 1, so that will be 2 perceptron that has to be in the hidden layer. And for 2 inputs, it's like 2 to the power 2, that is going to be 4 perceptron. And similarly, okay, if say 3, then that's going to be 2 to the power 3, that is like, okay, 8, and so on. And for n inputs, the total number of perceptron needed in the hidden layer is 2 to the power n. Okay. Let's see the multi-perceptron architecture. Okay, this is the multi-perceptron architecture. And we're going to see how this is going to solve the problem for XOR or XNOR. As for now, we'll just say for XOR. Okay, so a similar strategy will be applied for XNOR as well. Okay. Okay, so and we have already like discussed for different number of inputs, what would be the minimum number of perceptron needed in the hidden layer. So this is the hidden layer. Okay, so this is all of S4. Okay, this is one is input layer. This one is hidden layer. And this one is output layer. Okay, so this one is output layer. Okay, so for two inputs, so there are two inputs. The minimum number of perceptron in the hidden layer. In the hidden layer would be 2 to the power 2. That's going to be 4. So that's why I have drawn like 4 neuron over here. Not neuron. For now, let's say just perceptron. Okay, and I have like let's hand code the weight for the input layer. Okay, so these are not these parameters are not learned. Okay, so these are just hand coded. First, for simplicity in understanding the whole architecture, these are just the hand coded. Okay, so I have assumed the red line as the negative one and blue line as the positive one. So these are the weights. Okay, so this one is -1 and this one is -1 and this one is +1. Okay, so these are the hand-coded weights. Okay, and let's assume these are the H1, H2 to be the hidden perceptron, and okay, and then now this now the feature which are being learned now for the output layer. This X1 and X2 won't be the input. Now these 4 perceptron would be the inputs for this output layer. Okay, and there is one more line which is indicating for the bias. Okay, so this is the bias, and this is how like and finally we'll be getting this 0 or 1 indicating the whole this architecture would be okay, so let's not say like that. Okay, so just output is giving 0 or 1 indicating if this neuron is firing or not. Okay, so for different values of input and output, this whole so this has to fire for different for X, or it has to be like if X1 and X2 are like different. Okay, if it is 0 and 1 or 1 or 0, then the neuron should fire. So we don't need to worry about whether all of this perceptron in the hidden layer would fire or not fire. It doesn't matter. But for this input, this output perceptron needs to get fired. Okay, and for that we have to learn these weights. Okay, so now let's see the table. I have also drawn the table for the XOR. Okay, so let's so for different input values, so and we have defined the perceptron in the hidden layer as the H1, H2, H3, and we'll just for when X1 and X2 both are 0, then only this this perceptron has to fire, and for different other values of for X1 and X2, different neurons should be fired. But there should not be any option with 2 neurons fire at the same time. But so it can fire for different function, but for XOR we are just looking for XOR. So for that we have hand coded with this weight. So that's why only for one of the possibility, only one perceptron in the hidden layer should get fired. So that's why it has it's kind of like identity matrix. Okay, so only one perceptron in the hidden layer should fire for each pair of X1 and X2, and based on this then the output will get the output inequalities, or the condition to like the condition for output layer to fire output neuron to fire. So these are the condition. Okay, so here and these are the weights which we have to learn in order to get the XOR function. Okay, so W0, W1 to W4. So since there are like 4 neurons, these are the 5 weights, because one is coming from bias. So these are the 4 weights we have to learn. Okay, so there is only 4 inequalities. So, but there are like 5 unknown variables. So let's get one more function. Okay, so we have one condition y, like y equals to 0 or 1. Okay, so so it will a neuron will fire at the output layer when w. Okay, summation to 0 to n. Let's say 4, because we have just 4 neurons just in front of there are 4 neurons for input. That will be input for the output perceptron. Okay, so wi(xi) should be greater than or equals to 0, and this should be smaller than 0. Okay, wi(xi) should be smaller than 0. Okay, so we'll just assume this. We'll just take this one to get the another equation. Okay, so let's expand this equation. Like for neuron to fire, we have this condition. Okay, so let's expand this one. So it should be like minus W0 plus W1 H1. Okay, so for the output layer, H1, H2, S3, H1, S4 are the input. Okay, so that's why we'll be like changing with X with H plus W2 H2 plus W3 S3 is going to be greater than 0. Okay, for neuron to fire. Okay, still these are the hidden states, so we don't know, because we just want to get some equation in terms of X, X1 and X2. Okay, so we can like send this W0 to another direction, so that's going to be W1 H1 plus W. Okay, so I think there's one more missing, so that should be like W4 H4 is greater than or equals to 0. Okay, so similarly, I'm rearranging this equation. W3 H3 plus W4 H4 is greater than or equals to W0. Okay, so what is H1? Okay, so this H1 fires only when both X1 and X2 has the weight of -1. Okay, so that is going to be so here H1 would be negative X1, and this is the summation. Okay, because this perceptron has like summation over in this area, as well as there is some step function just to indicate if this neuron will fire or not fire. So for here it's like summation, so it's going to be minus X1 and X2. Okay, so if we look at this perceptron, and this perceptron will fire only when both the X1 and X2 are positive 1, so that's going to be X1 plus X2. Okay, so let's substitute the value for all these H or hidden perceptron. And, okay, we can expand this like for like W1 equals to minus X1 minus X2, so this will be minus X1 plus X2, and W3 would be X1 minus X2, and W4 would be X1 positive X2. This whole inequality should be greater than or equals to W0. Okay, so this is one more equation. So now we have got 5 inequalities. Okay, so this is 1, 2, 3, 4, and this one is 5, and we know the different values for X1 and X2. So we can substitute over here, and then we can go, or even we can get here like 4 other inequalities. Okay, if we substitute different value of x1 and x2, we'll get 4 different inequalities. So using all of this equation, we can assume the piecewise decision boundary for the XOR gate. So there are like 4 inequalities we have got over here, 4 inequalities we have got over here, and the unknown values are like 5. Okay, so 5 unknown variables. So I think we can now solve. We cannot get approximate value for W1, W2 because these are not the equalities, these are inequalities. So if there are inequalities, then there can be a lot of possibility for different possible values for all these weights. So we can just approximate the more approximate these weights to some optimal point, but it's like it's very tough to get with do it manually. So we just need some kind of optimization algorithm to learn these weights. Okay, okay, let's see now. Let's try to plot, observe graphically. Okay, so x1 and x2, and this is like 0 0 1 0 0 1 1 1. Okay, so for XOR, it should be neuron should fire only when x1 and x2 are different. Okay, so using all these equations with different lawn weights, we might come up with some kind of decision boundary that is non-linear. Okay, so here I'm not able to solve it, but I need some kind of I need some algorithm just to learn this with some optimization algorithm, but it should be something like this. So this is just my assumption. Okay, so it can be of any curve. I just need to see that, but for now, okay, so we'll get some kind of non-linear decision boundary. That's all. This can be like oval, circle. Okay, so it like that is going to be decided by different values of weights. Okay, so this is the region where our neuron will fire, output neuron will fire, and these are the region where our output neuron will not fire. Okay.